Right. Hi, everyone. We are going to get started on chapter 12. Can you believe we're already up to chapter 12? All right. Just fair warning, chapter 12 does step our game up just a bit. Like I mentioned in the beginning of the semester, as we progress um, through these different statistical tests, we build upon what we've learned in previous chapters. And this chapter, we are going to be learning how to perform um, an ANOVA test. Let me share here, which is, I would say, one of the more complicated types of tests to do in statistics. All right, so pay careful attention and, we'll get right through this. But make sure you have a very solid understanding of what variability is, and I have confidence that you do. That was way back in chapter 4, right? And with that, we learned how to perform sum of squares and calculate sample variance, and we learned what degrees of freedom are and why we use it. Also, you should feel pretty comfortable with what we learned in chapter 8 with regard to hypothesis testing and why we do that. And also, the uncertainty and errors that may occur when we are doing hypothesis testing, as well as the independent measures T statistic. I would say that ANOVA is builds upon that test quite significantly. All right, so it's sort of an extension of that in a way, and let's see how that works. So when we're talking about an independent measures t-test, we're comparing just two groups at a time, where we randomly select participants to either be in maybe a control group and an experimental group, or maybe they are in two other kinds of conditions. Maybe you're going to test, students from a morning class versus an evening class. So so the point is, you're with a t-test, an independent samples t-test, you are comparing two separate groups of people. Well, analysis of variance takes that a little further. This is where we have more than two groups of people, and we want to see if there's a difference between three or more individuals. You can do this test with two groups, but there's no point in doing so. We usually just reserve the t-test to do those analyses. So if you end up making comparisons between three randomly selected groups, this is where our analysis of variance, or ANOVA, comes in handy. All right. All right, so let's see here. So there's some terminology that we should understand when it comes to analysis of variance. We use the term factor, as you can see here, and when we're talking about analysis of variance, and really what we're referring to is an independent or quasi-independent variable, and it designates the groups that are being compared. So remember, or a quasi-independent variable are non-experimental variables like gender, or things a variable that has not been manipulated. Also, you should understand that just like independent variables that can have different levels or conditions that are related to it, like, an experimental and a control group, there are also levels of factors, which, maybe I am testing people's liking for different colors and how they perform, maybe well, people might do taking an exam in a blue room versus a yellow room versus a green room. And maybe color affects people's ability to concentrate. So that would be different conditions related to a factor in a design that would use analysis of variables or variance. So we call these factorial designs because there's typically more than two factors or more than two independent variables. And you can have uh, more than uh, you can have more than one independent variable as well. So not only can you have three or more groups in a factor, but you can have more than one factor or more than one independent variable. And this is sort of what it would look like if you were doing a factorial design with more than one factor. And this is sort of the simplest design. And here you can see they have two independent variables, and each independent variable has two conditions or two levels, right? And then here's, say you wanted to test, someone's performance based on the time of day, and there's two conditions, morning and evening, as well as whether or not they've consumed caffeine. And then you would compare their, performance on some measure, maybe taking exams, with taking both of these factors into account, okay? All right, so this chapter, however, will cover only one factor with three or more levels, all right? In our next chapter, for chapter 13, we're going to look at factorial ANOVA that includes two or more factors, okay? All right, so as far as hypothesis testing that goes for ANOVA, if you are stating the null hypothesis or the HO, the treatment conditions, it's saying that the treatment conditions have no effect on the participants' score. So it's saying that group means do not differ from each other. So it kind of takes all the possible groups or levels or conditions from your factor and says none of them are different from each other, right? And then the alternative hypothesis, it's saying that there's at least one mean difference among the populations, although it does not know or does not specify which one is different and what it's different from. So it just says that it's not HO, so it's not null, all right? And so the issue is once you've conducted an ANOVA test and say it's significant, it says that it's not HO, then comes the question of, well, which mean is different from the other, right? And there are tests that you perform to find out, which ones are different from others, all right? All right, so when it comes to tests of variance, and there are issues with the possibility of type 1 errors, right? So, of course, so might ask, well, why would we use an ANOVA when we can just compare all the possible, levels or groups 2 by 2, like, one group, compare it with another group, and then do all the possible combinations to see if there's a significant difference between them? Well, that's a good question. Experiments often require multiple hypothesis tests, and each of those tests, if you were to do a t-test, would have a certain amount of type 1 error or alpha level. And type 1 error for a set of tests will accumulate test-wise alpha and experiment-wise alpha. So when we say the term test-wise alpha, that's the alpha that you select for each individual hypothesis test. And then experiment-wise alpha is the total probability of a type 1 error that accumulates from all the separate tests done together. So every time you conduct another hypothesis test, you select an alpha level, and that actually will start increasing the amount of type 1 error that you would accumulate as you go. All right, so ANOVA evaluates all mean differences at the same time. regardless of the number of groups that you have. And so it avoids that inflated experiment-wise alpha. All right. All right. So here's another thing too. So if you think about it, it's really not possible to compute a sample mean difference between more than two samples, right? It doesn't make, say you have 3 levels or 3 groups in your factor. It doesn't make sense to say group 1 minus the mean of group 2 minus the mean of group 3. That doesn't compute, right? It doesn't make any sense. So that's why with analysis of variance, it's based on variance instead, hence the name, right? And we calculate an F ratio. All right, so variance is used to define and measure the size of the differences among your sample means. All right, and that is what is calculated in the numerator. So we're calculating variance for each group and then adding it together. How much difference or how much variance exists between all of the groups when compared together. All right, so you notice that the two variances provide an accurate representation of the size of the differences if you look. So if I look at, if I have 2 factors and I take the means from each group and I calculate the variance among these means, you can see for factor 1 that it's 58.33. And if I do the same for the other, it's 2.33. And if you look at the numbers, you know, and this is added together, and if you look at the numbers just visually, you can see there's a bigger difference between 20 and 30 and 35 when compared to 28, 30, and 31. It's smaller. So you can already start to see, yes, there is a difference between these groups, although we haven't stated which groups are different from others, right? All right, so in the ANOVA test, variance in the denominator measures the mean differences that would be expected if there's no treatment effect. It's called the error term, and it measures only the random and unsystematic variability or the noise that's within each sample. So now we're looking at variance within each sample and not the variance that exists between each sample. Hopefully that makes sense. And this is what we are dividing. All right, so let's look a little closer. The independent measures ANOVA partitions or divides the total variability into 2 components, between treatments and within treatments, just like I mentioned, right? So with the between treatments, which is in the numerator, variability results from general differences between the treatment conditions or the sample means, right? So remember, the factor will have, you know, at least three conditions or 3 groups, and we're looking at the variance that exists between each of these groups. We're not looking at how much variance exists within the group, each group, when it comes to looking at the numerator. That's when we look at the within groups variance for the denominator, and that's the within treatments variance. And of course, that captures the normal error or sample differences found within the population. We're not making any comparisons. It's like taking all of the scores and finding the variance between all those scores, right? There's and it's not comparing, you know, any differences between the groups. All right, so the value obtained for the F ratio, it determines whether any treatment effects exist. And there's 2 possibilities. There's no systematic treatment effects, and That means that the differences are entirely caused by random, unsystematic factors. So if the null is true, the size of treatment effect is near zero. So the F ratio would be near a 1, right? That means there's the same amount of variance within each treatment as there is between each treatment. So that's why the F ratio would end up being a 1. It means if I look at all the variance within each group and I divide that into the amount of variance that exists between each group, and it's exactly the same, that means there's no differences between your groups. So hence, if the F ratio is near 1, it indicates that the differences between treatments are random and unsystematic and equal to the amount of variance that exists within the treatments. All right. So then the treatment does have an effect and causes systematic differences between samples if the alternative hypothesis is true. So that means your F ratio is noticeably larger than 1. If it's only a little bit larger than 1, there's probably not enough difference or variance between your groups to really bring about significance, right? And so this would mean that the treatment effect is more than 0, if that makes sense. All right, let's do our first learning check. Is it true that ANOVA allows researchers to compare several treatment conditions without conducting several hypothesis tests? Also, is it true that if the null hypothesis is true, the F ratio for ANOVA is expected on average to have a value of 0? Right? You can pause it, see if you can guess correctly. And the first one is true. Several conditions can be compared in one test. So remember, we said it can compare 3 or more groups for your independent variable or your factor. The second part was false. If the null hypothesis is true, the F ratio will have a value near 1. We mentioned 0 because it means there's 0 effect, right? So that was a bit of a trick question, sort of, based on the terminology we were using. All right, so there's also some more, I guess, vocabulary we should remember. We've already learned that there's independent variables are now called factors, and these factors, like independent variables, can have several levels or conditions. There's also different notations that we need to remember for ANOVA formulas. So when we're talking about a treatment condition or a treatment level or a group, within your factor, we refer to that notation is referred to as K. So that's a group. So here for this example, we have K equals 3. The number of scores in each treatment would be designated as N1, N2. So it's numbering how many, the N is given a number for each person, right? So if it says N33, that's the 33rd person in that group. Also, the total number of scores is capitalized N versus a lowercase n that is referencing each score. So the total number of scores is N. When all the samples are the same size, your total N should equal the number of groups times N. Because remember, these lowercase n's are referring to the scores in each treatment. So if you have the same number of people in each group, like we see here, this has 1, 2, 3, 4, 5, 6 people in each group. And if I multiply 3 for 3 groups times 6, I will have the total number of N. All right, the sum of scores for each treatment condition is called a capital T. So if I add up all these scores, T will equals 30. The grand total of scores in a study is capital G, and that's just adding up each T, right? So if I add up 30 for this group, 54 for that, and 60 for that, the grand total is 144. Also, you should note that there's no universally accepted notation for ANOVA. Other books, other sources might use other symbols. So for our book, these are the symbols we're using. Here's the structure and sequence of calculations for the ANOVA. The final goal for calculating ANOVA is to calculate the F ratio, but first you need to calculate the sum of squares for the total, for the between groups, and for the within groups. And you also need to know what the degrees of freedom are for each of those areas as well. Once you've found the sum of squares for between, within, and total, you can calculate for variance. And once you've calculated for variance, you can finally find your F ratio. Right, so there's a lot of steps when it comes to ANOVA, and really ANOVA is not necessarily a hard thing to calculate. It's just there's a lot of steps to it. So I would recommend memorizing the formulas that are associated for all of the steps that are needed. All right, so here are the formulas that are related to sum of squares, right? So sum of squares, you would add up the square of each score and subtract it by the square of the grand total divided by total n. The sum of squares for between treatments is taking the total of the scores from each group, squaring it, and dividing by that group's total. And then you add that up. And then you subtract again by the grand total squared over total n. For within treatments, you just simply add up sum of squares for each of inside each treatment. Okay, and we'll look at the steps here on how to do that in a moment. All right, so also you need to figure out what the degrees of freedom for each of these categories are, and it's very different for each one. For the total degrees of freedom, it's the total n minus 1. For between treatments, it's the total number of groups minus 1. So if you have three groups, that would be 2. So 3 minus 1. For within treatment, you can take the total n minus the number of groups. Then you have to calculate the mean squares between, within, and then you can calculate the F ratio. And so you take that sum of squares that you've calculated for and divide by degrees of freedom. And you do that for the between condition and the within condition. All right. And once you find the mean squares for between and within, you can simply divide them and you have your F ratio. All right, so here's a little bit of practice. We're going to see how all this works. So step 1, you state the hypothesis and select the alpha level, just like our other tests. So say you have a researcher or you have researchers who wanted to compare the test scores for 3 different study strategies. And we have read and reread strategy, read then answer prepared questions strategy. We have a read then create and answer questions strategy. All right, so we want to know if there are any differences between these 3 conditions, and our alpha level will be 0.05. And remember, the null says that all the group means are equal, and the alternative hypothesis is that not all the means are equal. All right, so let's figure out what are the degrees of freedom for the total, between, and within. So for total, we take the total n minus 1. And so we had 18 people. Remember, there's 6 people in each group times 3. So that's 18 minus 1. So degrees of freedom total is 17. So between treatments, we have 3 conditions. Minus 1, that equals 2. Within treatments is the total n minus the number of conditions. 18 minus 3 equals 15. Then we need to find the critical region for step 2. So we use the within and the between treatments, degrees of freedom, to look up the critical regions. So we had the between treatments degrees of freedom is used as the numerator. All right, so that's what's up here on the top, which is kind of convenient because, you know, the numerator is, it will help you remember that, you know, the numerator top is between the degrees of freedom between. And then, of course, the within treatments is the denominator, right? So we found that the numerator is 2 and the denominator is 15. So our alpha level is 3.68 if we're using a 0.05 level. All right, we've underlined it there. So if our F statistic is greater than that, we can reject the null hypothesis. All right, here are the calculations. And up here you can see when we're calculating for sum of squares for each of those scenarios, for the between, within, and the total, how that can work. And if we look at the between treatments, you can see we take the total, square it, divide by n. Remember, that would be 6 because there's 6 people within each group. And then we subtract that by the grand total squared divided by n. So we can already see how the between treatments is looking at the differences between groups, which you should notice by that T right there, right? That's T is for the total of scores within the groups, and they're squaring it. Then the within treatment formula, so is basically just taking all of the sum of squares and then adding them up. So we're looking at all of it. So, well, let's first go to the total. So the sum of squares total is taking every square or every score squared, adding them up, and then subtracting that from the grand total squared divided by n. And you can see how we've calculated that. For the T, right, the groups, the between treatments here, we're taking each of the scores and adding them up. And then we will square it and end up putting them into the formula. So for each group, the added scores are 30, 54, and 60. So here we have 30, 54, and 60. And you can see we still need to square them and then divide by n. So there's 6 people in each group. And it's taking the grand total of the scores, right? We take all these scores, add them up, and the grand total is 144. That would get squared, and we divide by the total n. And you can see these groups are being subtracted from that grand total divided by n. We end up with 84. All right. So the next part for the within treatments, you can see we're taking the deviation scores, right? 2 minus 5. 5 is the mean, right, for each of those groups. And then we're squaring. So we found that for each group is 24, 34, and 30, right? And once we add those up, we have 88. All right. So for SS total, we're taking each score, squaring them and adding them up, and that happens to come to 134, and we're subtracting by that grand total again, and that equals 172. All right. You might have noticed that if we take the variant or the sum of squares and add them up, we arrive at 172. See how that can be considered the grand total? It's taking the total variance for between the groups and within the groups, right? So you can almost skip this formula. Don't tell anyone I said that. And just add up the variance for between and within, and you will have sum of squares total. I would say that the good reason for performing this analysis is to double check that your scores here were correct. Because if they are not adding up to this figure, then you've made a mistake somewhere. All right, so now we have calculated sum of squares between, within, a total, and now we can find the mean squares. So we simply divide. We already determined what degrees of freedom were for each of those areas, and we've determined sum of squares. So we take the sum of squares between divided by degrees of freedom between, and we arrive at 42. We do the same thing for the within, and we arrive at 5.87. And now we can take the mean squares for between and within and then divide them. And we end up with 7.16. All right. All right. So F turns out to be much greater than 3.68. So that means we can reject the null hypothesis that says that all the group means are the same. So the three conditions differed significantly on, I guess, I don't know why we have anxiety level. We were looking at study conditions. But anyway, so the group three conditions differed significantly on study conditions. And the way you would write this in APA format is just like that. And you can see that it gives the F statistic and it's italicized. And then it has a 2 and a 15. Well, where did that come from? Remember with the t-test, that was degrees of freedom, and we were looking at two groups, right? So we would take the total n and minus 2, and that would be our degrees of freedom. Well, now we're looking at degrees of freedom for the between and the within, which is put here. And I can tell how many people are in my study if I remember that there's a total number of groups minus total n, right, is degrees of freedom. So if I know that the number of treatment conditions minus 1 is the total between groups, I would say I can reverse that, the total number of groups plus 1, right? That would be 3. And if I know that there's 3 groups, I know that I can add 3 to this number, and that would tell me how many people are in the group. Okay. All right, so there is a video that you can watch to help you sort of, if you need to see that played more than once, how we arrive, how we step through the formula. You can continue, get a little more practice in. I'll put this in with the module on Canvas for you. All right. Just more practice, the better, especially with these ANOVA tests. All right, let's do our second learning check. Say we have analysis of variance and we perform an analysis of variance test and it produces a sum of squares total equals 80 and a sum of squares within and it equals 30. For this analysis, what is sum of squares between? How would you calculate that? I gave a little hint of that earlier. Hopefully you're paying attention. All right, let's check it out. So analysis of variance produces for SS between is 50, right? Because we had the total here, if we subtract the within sum of squares from that, whatever's left over would be the between. Remember, because we could add between and within and arrive at the total. All right. I will also, I've also placed some additional videos that helps you learn how to perform these calculations even more in Canvas in this module. And these are some Khan Academy videos, which I think are very helpful. So give them a look too. They might help you. All right, so here's some examples of hypothesis testing and effect size with ANOVA. I know you didn't think we would forget about effect size, right? All right, so if the null hypothesis is true, the value of F will be around 1, remember, because if you can divide the amount of variance that's within the treatments into the amount of variance that is between the treatments, and it's equal, then there's really no difference between your groups. All right, so because F ratios are computed from two variances, they will always end up to be positive numbers. And you should also know that the table of F values is organized by 2 degrees of freedom. The numerator, which is the between, and the denominator, which is within. And you can see that here. And here is the distribution of F ratios with within and between degrees of freedom. Of all the values in the distribution, only 5% are larger than F equals 3.68, and only 1% are larger than F equals 6.36. And you can see why these critical values are different from what we see in the t-test, because the shape of the F distribution is much different from the t-test. All right, so here's a review, an example of hypothesis testing and effect size with ANOVA. So hypothesis tests use the same 4 steps that have been used in earlier hypothesis tests, and we just went through that. This is just an overview. First, you state the hypothesis, select the alpha level, just like we do for all the tests, find the critical region, calculate the F statistic. That sounds so simple when you just say it in a cute little sentence like that, right? There's a lot of steps. All right, and then you can make your decision. And then you compute the test statistic in the different stages, right? We find some squares. We figure out what the degrees of freedom are, so we can then calculate mean squares and then compute the F statistic. All right. All right, so one of the ways a lot of people like to calculate ANOVA and sort of keep everything organized, because there's so many formulas you're doing, so many steps. It helps to create a summary table like the one you see right here, which I just messed up. And so we can keep track, okay, once you've calculated each of these outcomes for, sum of squares, degrees of freedom, and so on, you can kind of not get all mixed up. It helps you stay organized. And I've created this slide to help you you could probably print this out, which will help you, memorize the different formulas for each of these steps. And it'll be a handy, study. Oh, oops, I just knocked my phone over, sorry. It'd be handy for you for studying. All right, so back to effect size. We can compute the percentage of variance accounted for by the treatment conditions. And this is what is known as the effect size in ANOVA. And we call this eta squared, and it looks like so. It kind of looks like an N, but it's the Greek letter eta. And it's like the R squared concept that we use for t-tests. And it also tests the proportion of variance accounted for by the difference in treatments. And that is calculated using this formula, SS between treatments divided by SS total, right? All right. All right, so again, here is we already looked at reporting analysis of variance in APA format, but this you are also expected to report the N, the mean, and standard deviation for each of the treatment groups. So if you have 3, 4, 5 different conditions in your factor, you need to provide those statistics for each of those conditions. And it's always good to report whether or not you had significance in your ANOVA test, right? All right, the assumptions for the independent measures ANOVA. All right, so the assumptions are that the observations within each sample are independent. Also, the population from which the samples are selected must be normal. The populations from which the samples are selected must have equal variances. And this is referred to as homogeneity of variance. Try to say that 5 times fast. And this means that the quality of being similar or comparable in kind or nature exists between your groups. Also, violating that assumption of homogeneity of variance can risk invalid test results, and you can either end up with a false negative or a false positive. All right, so I did mention earlier, like the F-test compares all the mean differences simultaneously in one test, and that it does not tell us, well, which group is different from the others. And so what we do is we perform post hoc tests to make that distinction, all right? All right, so post hoc tests compare 2 individual means at a time. So it will take all the conditions that you have, all the possible comparisons that you have, and it tells you if there is a significant difference between any of those two, any two pairs. All right, so remember t-tests, with those we end up with accumulated type 1 error, right? So because of that, we risk making a false call. So we use post hoc tests, and they use a special method to try to control for this experiment-wise type 1 error. All right, and there's several different kinds of post hoc tests that you can perform. One of them is called the Tukey's, and it's well, the long word for it is Tukey's Honest Significance Difference Test. And it's a single value that determines the minimum difference between treatment means that is necessary to claim statistical significance. In this formula, the value for Q is found in the table provided on the, well, when I do this in person, I provide this test on my website, but I will have placed it in Canvas for you as well. So you'll see a link for that in there. You can also find it, of course, in MindCap. Here, Tukey's test requires that the sample size, N, so that in each group, be the same for all the treatments, right? So you have to have the same number of people in each of the groups, all right? And so you also need the degrees of freedom for MS within and the number of treatment groups. And then you select the alpha level. It's generally the same that was used for the ANOVA. And to be significant, the mean difference between any two samples must be greater than the Tukey's HSD test. And you can see how that is calculated with the formula here, which isn't too difficult, right? You've already calculated mean squares within, then you divide with the number of people that was in each treatment group. So if you had 6 people in each group, that would be 6. So 6 divided in this example into MS within, and then you find the square root to find Tukey's. All right, so here's an example, and you would do that for each of them, right? So You take, you've already calculated that, for example. All right, so we end up with 3.67. And then you take, oh, pardon me, the value for Q comes from the studentized range table. And so you take 3.67, and after you've calculated for the MS within divided by N, you put that in, you find the square root of that, and then you multiply. All right, so in this example, the mean difference between any two samples must be at least 3.63 to be significant. So then you make your comparisons. You take the mean from, in this example, we had three groups. You take the mean of group A and you subtract it by group B, and you find that it's 4. Well, that's higher than 3.63, so there is a significant difference. And here's the comparison between group A minus group C. That ended up being 5, so those two were significantly different from each other. But then the comparison between group B and minus group C ended up only being 1. There was no significant difference between those two groups. There's also, as far as effect size goes, oh, what is this? What's going on? I'm not sure. I'll have to delete that. All right, so there's also the Sheffi's test, all right? So this is calculated with the sum of squares of two groups. It's one of the safest of all possible post hoc tests. It uses and so, you know, it gives you more protection from committing a type 1 error. And it uses an F ratio to evaluate the significance of the difference between any two treatment conditions. It uses the F distribution tables, the same one you used for the ANOVA table, to test for significance. So for these, you also select an alpha level and degrees of freedom for within and between to find the F, which it should be the same as what you use for the ANOVA. Here, you know, and you should also note that sometimes the Tukey's test will find a significant difference between groups when the Sheffi's test will not. All right. So you can see the steps that you take to calculate you know, the significance for Sheffi's here. All right. So I also posted a video so you can see more in depth how to calculate the effect sizes for Tukey's and for Sheffi's. I'll put that in Canvas for you to help you practice. All right, so let's do learning check number 3. All right, which combination of factors is most likely to produce a large value for the F ratio? Oh, so now just think of it logically, right? When you're making a selection here. All right, so it will occur when there's a large mean differences and small sample variances, right? So if there's a lot of difference of variance between groups compared to the amount of variance within each group, you're more likely to find a significant F ratio. Also, is it true that post-tests are needed if the decision from an analysis of variance is fail to reject the null hypothesis? Also, is it true that if a report shows ANOVA results of F equals 5.32 with degrees of freedom of 2 and 27 and P less than 0.05, you can conclude that the study used a total of 30 participants. All right, let's see. The first one is false. Post hoc tests are needed only if you reject the null hypothesis when you're doing your initial ANOVA F test. right? Because if there is no significance when you're comparing variance from all of your groups, that's saying there's no difference between the means. So there's no reason to perform post hoc tests. All right, the last one is true. Because degrees of freedom total equals degrees of freedom between plus degrees of freedom within, and degrees of freedom total equals n minus 1, it would be n equals, or the degrees of freedom equals, or the total n is 30, like it mentions here, right? And we looked at that too. So hopefully you remember me mentioning that. All right, so more about ANOVA. The numerator of the F ratio always measures how much difference exists between the treatments. All right. I think we've kind of beat that one over the head, but just keep that in mind. And the denominator measures how much difference exists within the treatments. Here's kind of a visual representation of the between treatments variability and the within treatments variability. So here, so if we see the between treatments variability and the within treatments variability that form the numerator and the denominator of the ratio, we can see how there can be, significance versus non-significance. In the example of A here, the difference between the treatments is large and easy to see, right? The variance within the treatments is small, and the variance between the treatments is large, right? They're clearly separate from each other. There's no overlap. So because there's no overlap, that means the variance within the treatments is small. And because the two groups are clearly separate from one another, the variance between the treatments is large. All right, so in B, this has the same 4-point difference between the treatments. And you'll see that here, the mean for group A is 8. And the mean for group 2 or group B is 12, right? So 8, the mean here is 8, mean here is 12. Here, they have the same means for each group, 8 and 12, all right? But the within treatments variability is huge, right? And you know that because you can see how all the means are all scattered, or they're overlapping each other. And look, sum of squares for this one is 4, sum of squares for that one is 4. But here, sum of squares for the first treatment is 242, same with the other group. And so it's very difficult to distinguish any difference between these two conditions. Okay, so for two independent samples, you should note that either the T or the F can be used. So if you're calculating an ANOVA that has only two groups for its factor, it's essentially the same outcome. The result is really that F test that you will end up with is T squared. All right, so the T statistic compares distances with the F ratio, which compares variances. All right, and like we mentioned earlier, the distribution for T tests and F tests looks different. And you can see here's a the T test is symmetrical, and you can see that the F test is not, all right? So the critical values actually for the T are just the F squared, all right? Okay, the last few slides just give you step-by-step instructions on how to perform an independent samples ANOVA in SPSS. All right, so if you follow these steps using the data you have, providing that you are using the correct data, you should be able to conduct an ANOVA test in SPSS. And you'll notice dependence list. It has a continuous variable, which you should know that the little ruler here indicates that this variable is a continuous variable, or in SPSS, it's referred to scale. So that is the dependent variable. And the independent variable here is categorical. And you know that this is a categorical, but it's ordinal, right? So remember, the independent variable in ANOVA is called a factor, all right? And it shows you what additional things to include through your the options, right? And then here is an example of what kind of steps you would take if you, instead of were performing an independent measures ANOVA, or but wanted to do a repeated measures ANOVA, you would take these steps. It's a very different test. It means that instead of having, say if you had an ANOVA with 3 conditions and you had a different group for each condition, that would be an independent measures ANOVA, which is what we've been looking at in chapter 12 here. But what if you had an ANOVA where you had 3 conditions, but you had one group that experienced all 3 conditions? Then you have a repeated measures type of scenario, and you can perform a repeated measures ANOVA in SPSS, but many of the basic SPSS applications where you don't add anything fancy to it will not perform this test. So likely you as a student, if you're using SPSS from the school, or if you ordered the basic SPSS, you probably won't have this option in your SPSS. Okay. All right, that wraps up chapter 12, and I look forward to seeing you for chapter 13. Bye for now.